also good morning, and it's going to be quite a task to top, I'm not going to try even to top the previous talks that were great. This is a joint work with Iftach Heitner, or based on joint work with Iftach Heitner. I'm going to talk about, I'm going to show you that coin flipping protocols imply the existence of one-way functions. So let me start already with giving some intuition about coin tossing protocols. They were introduced by Blum in '83, and the study case he gave was that Alice and Bob are just recently divorced, and they live in different countries, and they want to toss a coin over the telephone to agree on who gets the car. Okay, so I'm going to present, like Ronen called it, a non-useful protocol, and hopefully we'll have a little less fun than we did with Ronen. Alice can simply toss a coin in her own private home and send it in the clear to Bob. And then both parties output this bit C. But obviously, Alice can be corrupt and desire the output to be 0, and in which case she can always send the bit equals 0, and she can fully control the output of the protocol. And we say that she has a bias of 1/2, because she can shift the distribution on the output by 1/2 from being uniform. So Blum in '83 already gave a much better protocol, assuming that commitment schemes exist. And I am also assuming that you know commitment schemes. Here, Alice samples a random coin, and rather than send the random coin to Bob, she sends a commitment to A. Bob, in return, samples a random bit, sends it back to Alice in the clear, and now Alice decommits to A, and both parties output A XOR B as their output. Unless one party is identified as being a cheater, in which case the other party outputs an abort. Sorry, outputs a special sign bot. Now, if Alice is corrupt and desires the output to be 0, indeed, she can learn that the output is not 0 before Bob learns it, but she can do nothing other than aborting unless she breaks the commitment scheme. And since we believe that, and then Gargamel goes home empty-handed as usual, and since we believe that breaking the commitment scheme can only happen with negligible probability, she can only bias the output of Bob with negligible probability of success. Sorry?
She can abort if she can see zero, so that will be either one or both.
No, so this is thank you very much for the question. This is the difference between the coin flipping protocols that I consider here than from the ones that Nikos talked about, which are fair coin flipping protocols. And I'm not talking about fair coin flipping. In my case, the honest party does not have to output a bit.
Either output 1 or both. You never output 0.
Yeah, but this is given, no abort, then...
No, given no both. It will be always one. Okay.
So the attacker wants to make something to be happening in either 0 or 1 with probability more than half.
Yes.
Is the attack model here? Yeah, so the attacker, in order to succeed, has to make either 0 or 1 to be sample with probability more than half, which doesn't happen here.
Yes, why am I confused?
What doesn't count? Doesn't count.
Better to stick to the definition and then we understand the
Okay, so let's go to the definition. No, but so a two-party efficient two-party protocol AB is delta bias if the probability in an honest execution of the output being 1 for both parties, or for the output being 0 for both parties, is equal to 1/2. And even in the face of a probabilistic polynomial time adversary, the adversary cannot bias the output, cannot cause the probability of the output of the honest party to be any bit b by more than 1/2 plus delta. And I'm still confused, I'm sorry.
This is correct.
It makes sense, but the protocol doesn't satisfy that.
That doesn't.
Why?
Because bot is not 0 or 1. So if you make it bot, it's not going to be an attack.
Yeah, okay, yes.
No, but
You cannot, okay.
She cannot make him output 0 with probability more than half percent.
Yes.
The output 0 with probability.
He cannot increase the probability of having 0. It's true that, sorry for my confusion. It's true that he can prevent the probability of having 1 altogether, but it cannot increase the probability of having 0. Okay, thank you. So we can also think about a weaker version where Alice knows that if she gets 0, she gets the car, and if the output is 1, Bob gets the car. And in this case, we should only protect against Alice desiring 0 and Bob desiring 1. And the fair coin tossing that Nikos talked about is a stronger primitive where the honest party must always output a bit. And in the most of this talk, I'm going to only talk about this definition, which is also known as strong delta bias coin flipping. Okay.
So if you would want this thing to be bounded also from below, to exclude like the previous thing, so
it's just right.
Yeah.
you get the same thing.
Okay. So obviously, coin flipping has numerous applications in secure multi-party computation, in zero knowledge. I'm going to mention it again. And by Blum's protocol and by Naor and Astad et al., from one-way functions, we can derive coin flipping. And the question I'm going to ask here is what is the cryptographic complexity of coin flipping? And specifically, can we have the other way as well? Can we derive one-way functions from coin flipping protocols? Why should we care, right? Coin flipping, why should we care about this problem in the first place? So the easy answer is because it's there. And to elaborate on that, coin flipping is an elementary and a fundamental primitive in multi-party computation. It's an important building block in multi-party computation. And moreover, it's a simple, basic task. And if you want to understand multi-party computation at all, you need to understand the basic tasks. And in retrospect, if you look back, the investigation of coin flipping protocols led to many very interesting research lines, very fruitful. I'm only citing the beginning of these lines. I'm not going to read them out loud. I want to go on. But here I'm going to focus on the cryptographic complexity of coin flipping, and I want to ask why this is interesting. And it's interesting because almost all computational cryptography was shown by Impagliazzo and Luby in '89 to imply one-way functions, but only almost all. And let me just recall what one-way functions are. They are functions that are easy to compute, but hard to invert on the average. Okay? Iftach already told you about them. Actually, much of what Iftach told you about is going to appear in the back scene of this talk. So coin flipping maybe, just maybe, a candidate for something that does not require the full power of one-way functions. And maybe we can settle for a worst case hardness or average case hardness. And this is a very interesting question, if we can have some cryptographic primitive that resides before the full one-way function power. Okay, so let me tell you about known results. I will actually go all the way to the current state of our knowledge. But let me first say that since one-way function imply coin flipping, then this area is already okay. If we are here, then we have coin flipping protocols. What about this section? Well, definitely, if you have the p-space power, then you cannot have any coin flipping, because coin flipping is a 0-1 game. You can apply the min-max theorem. And therefore, we need to understand this realm. So Impagliazzo and Luby showed that negligible bias coin flipping does imply one-way function. But here I'm going to focus on constant bias. So I'm asking for something weaker. Can I do that without one-way functions? So it's been 21 years until Maggi et al. Showed that if you have coin flipping, then P cannot be equal NP. So they colored this realm red. And in 2011, in a work together with Iftach, we showed that there is a constant 0.207, that if you have a constant bias coin flipping with that constant, then this already implies one-way functions. And I'm going to not read out loud the 1/poly factors. Finally, 3 years later, Berman, Heitner, and Tentes went the full leg for all constants. So they show that any constant, for any constant, if you have constant bias coin flipping, then you have one-way functions, meaning that constant bias coin flipping is not a good candidate. But this closed this question up to something that is less than constant. So I'm sorry, closer to 1 than a constant. And in this talk, I'm going to focus on this work, mostly because I know it and I co-authored it, but also because it serves as the basis for this talk, this work that is maybe even more complicated to present. But let me start with Impagliazzo and Luby. How do they go about showing that a negligible bias coin flipping implies one-way functions? So the main tool that they show, as Iftach already told you about, is that distributional one-way functions imply one-way functions, and therefore you can, given a transcript of the protocol, I'm not going to define the function. I'm going to be vague about it for a while. I'll tell you about the actual function later. But you can, given a transcript, you can sample almost uniform random coins for this transcript that agree with this transcript. And therefore, you can now suggest an attack using the notion of a game value that Nikos talked about, where the game value is the probability given a transcript so far that the output is going to be 1. And we know that the game value starts in any coin tossing protocol being 1/2 and ends up being either 0 or 1, and therefore there has to be a gap of at least 1/r. We can have a bigger gap, but I don't care about it. So you need to only find this gap. You can even guess the round number, and sample coins that agree with this transcript that you've seen so far, and take one that goes, if you look the whole way, the random coins, they also determine the output, that the output goes your way. And that's the whole attack. And from here on, you act honestly. You only attack the protocol once. You deviate from the distribution of the protocol once, but then you regain your honestness. And this is a single shot attack. It's a very nice feature to it that you, yeah?
I didn't understand the attack. What does the party do with sample coin? What does the sample coin?
No, so think you are party A. Either A can do it or B can do it. Okay, you guess a round number, and at this round number, you look at the transcript, you sample random coins that are consistent with this transcript, not only for you, but for both parties. And from here on, and furthermore, that these random coins lead to where you want to go, either to 0 or to 1. And from here on, you follow these random coins. Okay? It's not hard to show that you get a polynomial, 1/poly bias, 1/r, where r is the number of rounds. But let me tell you a bit about single-shot attacks. As I told you, they have the advantage that they are inherently efficient. You only sample random coins given the typical behavior of the protocol. However, they are also limited because of being a one-shot thing, and you cannot use them to bias the protocol by over 1/√r. And this can be shown using a simple example of the majority protocol, where parties interact in r rounds. In each round, they agree on a random bit together, and at the end of the protocol, they take these r rounds and take the majority of the r round, the r bits and the majority of the r bits. And it's easy to see that if the adversary can only tamper with one single bit along the way, he can only bias the output by 1/√r, order of. So let's, I'm ready now to talk about our work. And let me state the theorem again. We show that if you have a coin tossing protocol that is 0.207 bias, then one-way functions must exist. And the way to show it is by proving the following lemma. So we show that there are two efficient strategies, malicious strategies. I'm going to call it green A and green B, such that either when green A interacts with honest B, the output is 1 with probability 1/√2, or when honest A interacts with green B, the output is 1 with probability 1/2. And this already suffices for this for this result, because when you subtract, to get the bias, you subtract 1/2 from the actual probability, and you get exactly this value. So this is all I need to show you in order to prove my theorem, our theorem. And I want to emphasize that we do it for parties that wish the output to be 1. We can do the same thing. It's very easy to see that it's symmetric. You can do the same thing for 0. And actually, for this kind of attacks that can either attack towards 1 or towards 0, this is not only a lower bound, it's also an upper bound. You cannot do better with this kind of attacks. Okay, so how do you find an attack? First of all, we already know that it has to be a many-shot attack. You cannot use the one-shot thing. But then, once you decide that, you must be careful, because if you attack the protocol many times, you may reveal yourself as an attacker. You must be careful not to be too aggressive. Furthermore, if you are deviating from the distribution of the protocol by too much, then there would be no guarantee that you can invert the function anymore, that you can find a consistent random inputs, random coins. So this should be in our head for all times. So I'm going to describe the actual attack in a few slides. Before that, I want to give you some notations that are very useful when considering coin flipping protocols. And I'm going to talk about what not to do. So we like to talk about the protocol as being a tree of transcripts, where each node is the transcript defined by the path from the root to the node. And in our presentation, it's going to be useful to label each node by 2 values. The first value is the game value given the transcript so far. And the second value is the probability of getting there in an honest execution. Okay. So, sorry. The protocol, the full execution of the protocol defines the output. So you either have 0 leaves or you have 1 leaves. Yeah, that's what I said. Okay. So before going to the actual attack, I want to show you an example of a bad attack. It's a greedy attack. The greedy attack is an attack that in each round, what you're trying to do is to maximize the game value. So you see the partial transcript so far, and you estimate the game value given you're going to the right, given you're going to the left, and you take the maximum of those. And being such an attacker, you can actually very soon lose control over the protocol. So think of the case where Alice is the attacker. She controls the first message, and she sees that the game value here is 1 minus epsilon. The game value here is 1 plus epsilon. The greedy attack says go to the right. But what happens is that the protocol decides that here Bob takes control over the protocol. He decides the output, and therefore Alice cannot deviate again and again. She's back to the one-shot attack. Furthermore, even if this is not the case, if Alice say beta is really large, it's almost 1. So even in the honest execution, you ever go here with very, very small probability. So once you got here, you don't know if you can invert the function anymore. So even if she has control, she cannot apply the function anymore, the attack anymore. Okay, so this is something we should avoid. We cannot be too aggressive. We should be gentle with the attack. We should not deviate from the distribution by too much. And actually, so I'm not now going to show you the actual attack, and it's called the bias continuation attack. Let's define A, green A, as follows. So I'm going to define an ideal attacker. This ideal attacker on a transcript alpha, this is alpha, what she does is sample uniform, actually fully uniform random coins that are consistent with alpha, and moreover, they lead to a one leaf. And this is what she does at any point in the protocol. And the next message she sends is according to these random coins and what the honest A would do with these random coins, given that alpha was a transcript so far. Okay, and so this is a many-shot attack. And the nice thing that I will be able to show you that A does not deviate by too much from the actual distribution. But is it efficient? Well, it's not efficient because we cannot sample really uniform random coins. But this is the least of our problems. The actual problem is that even the ideal attacker deviates slowly but surely from the actual protocol, and it cannot always invert the function even if random coins exist that lead to that comply with these requirements. But still, let's talk about the ideal version. I'll tell you about the efficient version later on. So what is the claim that we want to prove about this attack? We want to prove the following, that either green A with honest B can cause the output to be 1 with probability 1 over square root of 2, or green B with honest A can do the same. Either of them. Okay, so I just want to mention that this bias continuation attack already appeared in the realm of parallel repetition in the work of Hastad et al. So let me tell you about how we go about proving this lemma. We consider the execution of the protocol. We consider 3 new protocols. One, where Alice is malicious, Bob is honest. Second, when Alice is honest, Bob is malicious. This is very common, but the interesting thing we do is also consider a protocol where both are malicious. And not only they are malicious, they both want the output to be 1. Okay, so they work together. And the idea is to show that even in this case, we do not deviate by too much too soon. Okay? So this is done by proving a lemma which we call the compensation lemma, stating that the probability of falling into any partial frontier, where a partial frontier is a set of nodes where there is no couple that one is the ancestor of the other. Okay, so for every partial frontier, you get that the probability of the all honest execution times the probability of the all malicious execution to fall in this partial frontier is the same as when you multiply the probability of falling when A is malicious as B is honest, or when A is honest and B is malicious. And given that let's not see the proof just yet. Let's assume that we have this lemma proved and see how it implies the main lemma or the main claim. So this is the claim that we wanted to prove. We have this lemma and define the partial frontier to be the frontier of all one leaves. Okay? So what is the probability of falling into this partial frontier with the all honest execution? It's 1/2, just by the definition of the protocol. What is the probability of falling there with the all malicious execution? All cheating execution? Well, it's 1, because both parties work together. They always have a pre-image because they always go towards 1. And they are ideal. So it turns out that this is 1/2, namely either should be at least 1/√2. And then we're done. This is the whole proof for the ideal case, given that we have the compensation lemma. So let's see the compensation lemma. This is the compensation lemma. How do we go about proving it? So let's prove it for the simple case of a single node, a single transcript. So we have that the probability of going to 0, 1 is simply the probability of going to 0, and then from 0 going to 0, 1. This is the same for any protocol, also for the all cheating execution. And the point to notice is that since Alice controls the first round and Bob the second round, it only depends on Alice what happens here. So she doesn't know if B is being honest or not. And similarly here, Bob doesn't know if Alice is being honest or not. It goes both for honest Bob and cheating Bob. And therefore, we have that the probability of honest A with B going to 0 is the same as honest A with honest B, and honest A with malicious B is the same probability for, given that we visited 0, we went left on the first round to go right on the second round. It's the same probability whether Alice is malicious or Alice is honest. And therefore, we get this probability from, it's the same argument like here, but I replaced probability of honest A, malicious B, and honest A and malicious B with, according to these two values. Similarly, you get this. And therefore, you see that when you multiply these two, you get these 4 multiplicants. And when you multiply these two, you get the same 4 multiplicants. And you're done. This is the compensation lemma. OK? So we've seen that the ideal attacker does really well. And now let's try to talk about an efficient attacker. So let's define an efficient attacker. And this is the first time I'm going to define the actual function I want to invert. The function is a function that takes randomness for A, randomness for B, and a round number. This round number is only a technicality. And it gives out, what does it give? It gives, so this randomness gives you a full transcript, a full path in the tree. So the first thing I'm going to take is the partial transcript of length I, and the second output is the value of the leaf. Is it one leaf or is it a 0 leaf? And now by Pagliazzo and Luby, I can invert this function as close as to uniform as I want. Okay? So now let's define the efficient adversary, this is the ideal adversary. Where do we need to change it in order to obtain an efficient adversary? Well, first of all, we need to change all this because we cannot sample uniform random coins anymore, but we can invert the function. So first of all, we invert the function. We use this inverter, and then, as I told you, this is also a problem because I may arrive at a point that I cannot invert the function at all. Even if there exists a pre-image, I cannot invert it. So what can I do? I can simply fail. If the inverter fails, I fail. Okay? And we'll show that this is good enough. Yeah. So I want to emphasize that this problem doesn't only appear, I already said that, but it doesn't only appear when the adversary is efficient. It already appears when the adversary is ideal. Just by the mere fact that you attack the protocol over and over again, you deviate from the protocol. But we will see that we can do well enough even if we fail on all non-typical nodes. Really? Wow. I have almost 10 minutes. Anyways, thank you, sorry. So what are the non-typical nodes that we need to face? Let's talk about them. So there are two types of non-typical nodes. First is the unbalanced nodes. What are unbalanced nodes? So let's talk about unbalanced nodes for A. Here I'm just reminding you what the function is and what the type of queries that we have is. We have queries that have a transcript and an output value. Okay, so what are unbalanced queries? There are queries of this form where alpha is a node that Alice may get to this node with much higher probability than in an honest execution. Namely, in an execution where Alice is malicious and Bob is honest, you get to this alpha with higher probability, say 1,000 times much higher. And also, I'm going to define this frontier, so there are no two nodes here that are, one is the ancestor of the other. So this is a problem. Why is this a problem? Because if simply by taking probability of green A, blue B to arrive at alpha being 1, you get that the probability of the function ever ending there, or the protocol ever coming to this frontier, is at most 1 over C. So it's too small. Maybe we cannot invert the function. Second type of non-typical queries are queries that they have really low value. And if I'm trying to invert the function having the output being 1, how can I have a big probability of, a large probability of ending in a low value node? So this is also not going to happen. But other than this, we can show, I'm not going to show it to you now, but other than this, the set of all other nodes or queries is dominated by the actual output distribution, and therefore we can invert them quite well. So we only need to deal with these two types. I'm only going to show you how to deal with this one. And to do that, I'm going to tell you something about the old cheating execution. Actually, the other type is handled very similarly. So what am I going to tell you? I'm going to tell you that this attack, that this protocol does not deviate too much from the actual distribution. Specifically, recall that V of alpha is the game value, and W of alpha is the probability in an honest execution to arrive to alpha. And I'm going to tell you the following. The probability of the all cheating execution arriving at alpha is at most twice the probability of arriving there in an all honest execution. And let me show you this quickly. I'm going to show you only for the simple case where the probability of going either left or right is always 1/2. Therefore, arriving at a leaf is simply a uniform peak over the tree. Okay, and yeah, I'm going to really skim through this really quickly. And you can see that what we can prove is that the probability of green A, green B arriving at alpha is twice the game value of alpha times the probability of arriving there in an honest execution. But since this is at most 1, we get the claim. Okay? So let me state it again. Probability of every node in the all cheating execution is at most twice the probability in an all honest node. So how do we deal with unbalanced queries? This is the partial frontier of unbalanced queries. First of all, the probability, we've already seen that the probability of all honest falling there is 1/c. Now, by what we just proved, the probability of all cheating getting there is at most 2/c. And I'm going to assume that the probability of green A, blue B getting there is at most 1/c, because if it's not, at least 1/c, because if it's not, then I don't have a problem. I rarely get there. I don't care if I fail. But if I do get there with green A, blue B, then by applying the compensation lemma, we get that the probability of getting there in a blue A, green B, when B is attacking the protocol, is also quite small. And therefore, what I can do is take each node that is unbalanced and look at the sub-protocol or sub-tree below it and simply trim it. Think about a protocol where I give the control over this node to B, and B either goes left with probability delta or goes right with probability 1 or minus delta, which is the actual game value. And I'm going to now consider this protocol. The nice thing about this protocol is that it's still a coin tossing protocol. And therefore, everything we proved so far is still holds. So that means that the ideal strategies can attack this protocol. Furthermore, the malicious part is, until this point, until reaching to this node, they behave exactly the same. So on all other nodes, they have the same success probability. And here we can show that since B hardly ever gets here, he doesn't gain too much by considering this protocol. And Alice, the malicious Alice, what we can say, we can ask her, when you get here, well, you're in a problem. You don't know how to invert the function. What you do is you just behave with the last random coins that you have honestly until the end. And she does exactly yeah, sorry. 1 minute, okay. So this is enough to cope with this. I'm just going to tell you one word, not one, 3 words about the follow-up work by Berman et al. They showed that any bias, any epsilon bias coin flipping protocol implies one-way functions. They have the same scheme. They have not the same skeleton. They have an ideal inverter that actually applies our inverter, our attacker, iteratively a constant k number of times. Then they have to talk about an efficient inverter. They have a technique called the pruning in the head attack, where they trim all values, all nodes that are too close to 0 or too close to 1. And the success analysis is very challenging, but I will say two things. Okay. I won't say two things. I'll say thank you. So to summarize, they showed, that any constant bias coin flipping implies one-way function, and the challenge is to close the gap to any non-trivial coin flipping. I think I was, yeah. Thank you.